Good afternoon and welcome to the next lecture, which is about state feedback control. In this lecture, the content is very long. For today, I will only discuss state feedback, and maybe it will last couple hours until next week, next class. So before I introduce the concept of feedback, state feedback control, let's review the state space representation that you can model from ordinary differential equations. For example, here, suppose you are given a second order ordinary differential equation of a DC motor, as you can see here. In here, VA is the input voltage to the motor, theta is the output motor angle, and A and B are assumed to be constant. Then this equation can be transformed into state space form, as you can see here. And now you are asked to find A, B, C, and D. Let's exercise this to recall what you learned a couple of weeks ago. Okay, so let's try. Okay, just in case you don't remember what you learned before, let me give some hint. So in this equation, it is called state variables, and actually you have H1 and H2, and you need to relate it to theta and theta dot. Okay, and Y is actually the output of this equation. So Y is output, then it means Y is just theta. Okay, and U is input. Okay, U is input, then U actually is just VA. So now you try yourself how you introduce H1 and H2 related to theta and theta dot, and then find two equations in terms of H1 and H2. I can say, well, I can give more hints. So in here, it's like H1 dot, H2 dot, and you have A times H, which is well, for H1, H2 here, and A you have element like A11, A2, A12, A21, A22. Okay, and B you have B11, B21 times U. Okay, and for Y is scalar, so C is supposed to have one row only, right? And you have Y, and C here you have C 11, C 12 times H1, H2, and plus D, because D U is scalar, then D is also scalar. Right? Yes. D is also scalar. So just D times U. Okay, just D1, D or D11. Yeah, you can just use D, just like this. So now you need to find A, B, C, and D. Okay, so let's try for a couple of minutes. Okay, so I'll do it quickly. First, let h1 equal to theta and h2 equal to theta dot. Then the first equation is h1 dot equal to h2, which is 0, 1 times h1 and h2, like this. Then h2 dot equal to theta double dot. From the equation here, theta double dot equal to minus a times theta dot, but theta dot is h2, plus b times va, and let va equal to u, or u equal to va here. So here we can have b times u, and here you can rewrite as, because there's no h1, you can write 0 minus a times h1 and h2, right? Plus b here, still bu, and then okay, for this one you can also write 0 u, right? Then we can concatenate these two equations. So h1 dot h2 dot equal to 0 here, 0 here, 0, 0, 1 minus a, 1 minus a times h1, h2, plus 0 here, and then b here times u. Okay, and then y is the output, which is theta, and theta is h1, right? So actually it's just 1, 0 times h1, h2, right? And you don't have u for the equation of y, so you can rewrite as y equal to 1, 0, h1, h2 plus 0 u. Therefore a equal to 0, 0, 1 minus a, b equal to 0 b, c equal to 1, 0, and d equal to just 0, right? Okay, now you already have state space form, which is this one, and so for any linear system, first order, second order, third order, you can always transform it into state space form like this. H dot equal to AX plus BU, Y equal to CH plus DU. Okay. Next, you still want to? Okay. Actually, it's not very difficult, but you just need to get the key steps. Step 1, step 2, and step 3. Step 1, let H1 and H2 in this way. Okay. Step 2, relate H1 and H2 from the how you relate H1 and with theta and H2 with theta dot, right? And then yeah, you already get the some equation by just relating H1 and H2 according to theta and theta dot. If you have higher order, if third order, then you have H3 equal to theta double dot. Then you can easily relate, and you can have a bunch of equations just from their relationship of time derivative. But then the last equation that you can get is to find from here. The last variable h, you take time derivative, then you will get the highest order of time derivative, and then you can relate all other parameters from the dynamic equation here. Okay, just get some key points like that, then it's gonna be very easy. So okay, now let's consider state feedback control design. Okay. Again, here from physical system, you make modeling. Sometimes you can get state space form directly, or sometimes you get ordinary differential equation, right? But anyway, finally you can always transform the model into state space. For some equation, yeah, it might be non-linear, but then you need to do linearization, but it is another topic that you are going to see a couple of weeks later. But anyway, for many systems, you can automatically get many systems are linear. Then when you transform from ordinary differential equation into state space, you already get this linear form. Okay. For stability or reachability, well, there is a way to analyze on the original equation if it's non-linear, but if it's linear, we have a simpler way to analyze the reachability. Okay. If the system is reachable or the system is controllable, so this one is just equivalent to controllable, then we can have a way to find controller, which means to design a controller. And in the process of design, we may need to use tuning some parameter to see the performance, how much it overshoot, what is the settling time, what is the rise time, something like that. We tune parameter to get the desired performance. Okay. Okay. So here I don't talk too much on linearization and reachability because I will introduce later. Now let's assume equation that we have is already linear and already controllable. Then let's consider a control method. How can we control a system with model a state space form like this? So we have state equation. So remember again, this is state equation. And this one is output equation. When we say output equation, it means we can measure this one. Okay? Why can be measured? and from this equation y can be computed, right? Can be can be predicted, right, by computation. So in some sense, you can have comparison of predicted output and the measure output, right? In some sense you can have this. That is about practical, practice on actual system if we need to do experiment. So now let's work on simulation. The simulation that we can compute H as long as we know the constant A and B and the initial state H and the input U, right? We can compute H and then we can compute Y, okay, for simulation. And for this model, H can be can have as high dimension as possible. It depends on the system you have, and input can be also can also have high dimension up to p dimension, for example, right? And output, well, some variable or parameter that you can measure can have higher dimension as well. And one idea is that in order to control the system, you need to modify eigenvalue of A, but A here does not mean this A, because this A is constant. A here means the coefficient of H, because let's say if you choose U in terms of H, right? If U in terms of H, for example, minus KH, then you can take H as a factor, then you have something as a coefficient of H, and that way you can modify the eigenvalue. Okay, this is one idea if you are still familiar with eigenvalue. Well, as you can see here, state feedback. State feedback means you choose U, the input, in terms of state itself, right? So here U equal to minus K times H plus KR times RT. RT is referent, or equivalent to desired output. Like the example previously, the output is the angle, motor angle. Then desired output means desired angle, like how much angle you want the motor to rotate. Like let's say you want it to rotate to 90 degrees, or you want it to rotate one round or one turn, so it means 2 pi, right? That is desired output or reference, right? So you desire this value and then you choose the right value of control input, then you expect the actual output Y approach to the reference, right? It means you choose desired of T. Let's say you choose desired a step like this, and you expect the actual output Y to no, not good. Something like this, right? let's say at the steady state you have output y approach to R. Okay, this is the idea of control. So anyway, here what you want is y converge to reference R, and at the same time you need to have stable state of state H, right? Stable means converge, H also converge, because y converge, it has to be converged as well, right? So how can we show that H converge? Okay. Well, we look at the equation. We substitute u by this term into the state equation. Well, okay, before I elaborate the equation, let's see the block diagram that we can use to make simulation. Yeah, this block diagram is just for simulation. I will elaborate the conversion by how we choose the right value of k and value of kr later. So here, let's assume that we know A, B, C, D, K and KR. We desired reference R is lowercase r here. Then we can simulate it to find Y. Okay. So block diagram here. When you want to draw this, you start with the state equation. Start with H. When you have H dot, you just integrate. Maybe you can also use, well, actually you can also use 1 over S here. It's not a problem. You integrate, you get H. And you have H dot equal to AH plus BU, right? So you already have H, you just multiply H by A. And then you add U multiplied by B, right? U left multiplied by B, something like that. Okay. So U times B plus H times A equal to H dot here, right? And then H times C plus U times D here equal to Y, right? Because Y here equal to C times H plus D times U. So you can see here is H times C, here is CH, right? And then here, because here is U times D, you have DU here. Okay? Yeah, I can write, okay, you have H here and H as input, and you have gain A. Oh, this one is mistake, eh? This one is a mistake. It's like this. Okay? So here is AH and here is BU. So AH plus BU equal to H dot. How about U? U is defined as state feedback minus K times H plus KR times R. Okay, R of T. Yeah, just R. So here is H. Then H is input of this gain minus K. The output here is K minus K times H, right? And then plus here KR times R, which is U. Yeah. Okay. So from this illustration, I hope you can build a simulation model in Scilab or Simulink, right? Okay. Well, so now we know how to make simulation once we know all the parameters. And here for the dynamic system we know A, B, C, D. And now we need to choose the right K and KR in order to have the system stable, right? And okay, let me elaborate. Once you choose U, here is U, then you can substitute U into the equation, into the state equation. You can have this, and then you can separate H and RT like this. Then the coefficient of H is A minus BK. Let's just call it a calligraph. Okay. And while for differential equation, okay, system differential equations like this, because RT is just some known function that we cannot do anything with it, right? It's already given, right? And suppose let's assume that RT is just a convergent function. Then, yeah, a convergent function. Then we analyze, we try to find K such that H converge at the steady state. Okay, we want H at steady state converge. How? What is the condition that H converge if we have differential equation H dot equal to A calligraph times H plus something? Okay.
Means that all the terms that depends on T should equal to 0 when T goes to infinity.
What equal to 0?
The terms that depends on T.
This term?
Otherwise, it will never be. It will never reach steady state. For example, x of t and r of t.
Well, let's see just first order. Okay, just make analogy. We will expand the first order to high order, but let's see first order first. Let's say you have just h1 dot equal to minus 2h plus, just say a constant or step, let's say just 2 as well. Do you think this system converge? I mean H converge? Look at the homogeneous solution. Homogeneous solution is exponential of minus 2t, right? Right? So this term converge or not? Yes, so this one converge. It go to 0 when t tend to infinity. This one you don't need to care it because it's a converged function or known. The most important thing is the homogeneous solution. Okay? Homogeneous solution decide whether the system is stable or unstable. Particular solution, it just depends on the input. Okay? And okay, let's say you also have h2 dot here equal to just let's say minus 3h2 plus 0. For this term you also have e minus 3t, so also converge when t tends to infinity, right? So the key point here is that the coefficient of h1, coefficient of h2 are negative, right? In order to have it converge. But if you write in terms of in the form of matrix, you have h1 dot equal to h1 dot h2 dot equal to minus 2, 0, 0, minus 3, h1, h2, right? Look here, suppose this is just a calligraph. Now you can see the pattern or the idea that in order to have this differential higher dimension differential equation converge, you need, for this specific case, eigenvalue, diagonal value negative, all diagonal value negative, right? But what if a calligraph is not diagonal matrix? What is the condition that you need to have in order for the system to converge? It's not diagonal, not diagonal like this.
What's the condition for it to be?
So for this example, so this is just example. If you have system like this, the H1 and H2 are converged, right? And if you want to write this into matrix form, you get diagonal matrix like this. Okay. Okay. So it is easy to say if you have A as diagonal, you need all diagonal value are negative. Yeah, to be negative. What if this A is not diagonal matrix? Let's say you have this value, this is not 0. Let's say you have 1, 2, minus 2, 1. No, maybe 1 here, 1 here. Like this. Yeah. Let's say it's like this. So then, yeah, if a calligraph is like this, can we conclude that H1 and H2 converge? No, we cannot conclude that, right? Even though diagonal are negative, but we also have off diagonal value, we don't know, right? We don't know whether it's converged or not. And then the condition to ensure condition that we must have so that H1 and H2 are converged is that eigenvalue of the matrix A must be negative. Yeah, all of the eigenvalue must be negative.
For it to converge? For it to converge?
For?
If the eigenvalues are negative, it will always converge?
Always converge. Yes. So I should use this symbol, all eigenvalue of A are negative. Okay. And let's recall the system of the ordinary differential equation. In order to have the what is the condition that an ordinary differential equations converge? Okay, what is the condition that we need to have so that ordinary differential equation converge? No, if let's recall ordinary differential equation. Let's say theta double dot plus A theta dot plus B theta equal to 2. Just say C. What is the condition that the solution theta to be converged? Characteristic equation has if we convert if we use transfer function, what is the condition that the system to be stable? If you use transfer function,
The transfer function needs to be inferior
Yeah, you remember the poles?
Yeah.
All the pole has to be,
On the left hand side.
yeah, left hand side of the complex plane. Or we can say the real part, real part of all the poles need to be negative. And if you relate those poles with eigenvalue, you know what? They are just same. Let's say if you transform the ordinary differential equation into state space, condition for ordinary differential equation is that all the real part of the poles must be negative. And for the state space representation, you need all real part of eigenvalue must be negative. And these eigenvalues are just same as the poles. Okay? Yeah. Well, I think in order to have you understand deeply, I will wait. What should I do? I will illustrate what I just explained later. Yeah, soon later. I mean, when we have ordinary differential equation and then transform into state space, one way we find the characteristic equation, another way we will find eigenvalue, and we hope that the characteristic equation and equation for eigenvalue are just the same, right? Yeah, I will illustrate it later. Now, what time is it? Okay, now you can take a break about 5 minutes.